Welcome to Physical Attacks and Countermeasures, the last session. We deal with fault injection attacks and we also see some countermeasures, how to provide security against these kind of attacks. What are the fault attacks? You have seen a very simple idea of fault attacks. If you remember, it was one of the first sessions that we said we can inject fault into the system. We can make some difficulties for the computation inside the circuit or microcontroller, FPGA, ASIC, in a way that the computation is not correct. And we have seen as an example that you can bypass the pin checking of one simple microcontroller. There was no cryptographic algorithm involved. It was just pin checking. Now we get a bit deeper and see how we can use these attacks to really break implementation of cryptographic algorithms, particularly symmetric crypto AES. As I said, the idea is to find a secret which is used by the computation by inducing transient faults. The faults that we inject into the system, and usually they are transient. You should keep in your mind there are two types of faults that you can inject into the systems. Some of them are transient, means that you inject the fault, the computation is incorrect, but the next encryption or decryption or computation of the circuit becomes completely normal. Because some wrong values are stored in the register, and this is the wrong result of the computation. But then if you do not induce the same fault again, then the computation will be correct for the next encryption. But there are also some permanent faults that you can inject. For example, by some laser beams, you can destroy part of the circuit. Some gates you can destroy, and afterwards this gate does not work anymore correctly. And with some inputs, the output of the gate will be wrong, and then it doesn't matter how many times you give the same plaintext to the system, then usually the same faulty output comes out, if you injected some kind of permanent fault. But what are the typical scenarios to perform the attack? The attacker gets the output of an encryption for a plaintext, and then she gets a faulty ciphertext for the same plaintext while inducing the fault. It means that once you get the fault-free output, fault-free output that we usually call it clear ciphertext or correct ciphertext. And the other one, the other ciphertext that you get is a faulty ciphertext for the same plaintext. It means that you need to give one plaintext to the system 2 times at least. Once without any fault injection and the second time when you are inducing the fault. And then usually we need to consider a specific model for the fault. Means that we say at one position, at one byte and 1 bit, the fault is induced. We will discuss about this, but we have to model the fault, and we have to consider a model, either a very specific or a very general model for the fault. Without considering any model for the fault, we cannot perform any attack. For that reason, when you have to compare the faulty ciphertext with the fault-free ciphertext, this is called differential fault attack, or DFA. And we will see this later. If you have any information and experience with differential cryptanalysis, which is a known attack scenario to perform attack on symmetric ciphers, not implementation of symmetric ciphers, really on the symmetric ciphers. Differential cryptanalysis, DFA or differential fault attack is seen somehow as a differential cryptanalysis on a round reduced cipher. It means that you have just 1 round or 2 rounds of the AES, and this 1 or 2 rounds of the AES, of course, is vulnerable to differential cryptanalysis, and then by using or injecting some faults, you somehow turn the problem of performing the attack on the cipher or on the implementation to a differential cryptanalysis on a round reduced version of the cipher. The type of the faults and the position within the algorithm changes the strength of the attack. Sometimes you can perform the attack with super simple models, which are general. Means that you don't need to consider a very specific model. But for some other attacks, you need a very, very specific model to perform the attack. Means that you should control where you can inject the fault, or you can completely control the effect of the fault on the implementation. And when we say the strength of the attack, it means how many pairs of the plain text and faulty ciphertext you need to perform the attack. And sometimes you need a particular fault to be injected into the system, and then you need to, for example, thousands of such pairs of plain text and ciphertext, but injecting such a fault, such a precise fault, again and again with exact the same position or under the same model might be not that easy. If you have a very specific model to inject a fault, then you should have also a very low number of pairs of plain text and ciphertext to perform the attack. It means that if the model is very specified, and you need many pairs of ciphertext and faulty ciphertext, then the attack becomes very, very hard. Because injecting the same fault again and again to get many pairs of ciphertext and faulty ciphertext is not that easy. Sometimes in the literature you see faulty text instead of faulty ciphertext. Just the difference in the terminology. Good. We have seen how to inject the faults before. We discussed about this, but a bit more I explain here for you that what are the power glitch and the other means to perform the attack. This is what you have learned. There is a device, and this is the VDD, and this is the ground, and if this is the time domain, and this is, for example, VDD. For example, it should be at 1.1 volt, all the time. This should be, for example, the voltage of the crypto device, and then for one particular time, for example, at here, you reduce the power somehow up to a certain level and for a particular duration. And then you play with these values, with these parameters, how much it decreased and how long is this glitch. Then you may reach exactly what you want. Sometimes, particularly for microcontrollers, you may skip an instruction. Means that the instruction is there, the program counter is increased, but the instruction result is not stored in any register. Sometimes. And it depends on the value of here, this value, and also this duration. And I have to say that in reality, this will not be like this. If you inject such a fault, it will be something like this. It happens like this. And then, of course, this is the same duration. And the level of voltage, of course, is important. And this is called power glitch. And another one is clock glitch. This guy needs a clock, and if the clock is provided from the outside, the normal clock will be something like this. And of course, you learned this before, that this duration, if the circuit works at the positive edge of the clock, this duration, let's call it small d, this d should be longer than the critical path delay of the circuit. The circuit works correctly. But if you make the clock in a way that it goes up and again goes up, for example, like this, which is synchron afterwards with the main clock, then you reduce only one cycle. This is d prime, and then d prime is smaller than d, and of course smaller than the critical path delay. Then for some inputs of the circuit, you have the circuit. If you model it as a combinational circuit which drives a register, if you remember, you have a melee and more machine, it doesn't matter, one of them. Then if you reduce this period of d to d prime, then this combinational circuit may not have the output ready to be stored in the register. Then the wrong values will be stored in the register. And this is the clock glitch, and of course the duration of this clock is also important. If it's a little smaller than the critical path delay, for most of the inputs of the circuit, it's fault-free without any problem, but for very few of them it will be problematic. And then you may inject the fault and you may directly explode what are the values which are stored in the register. I have to say most of the devices that I know in practice, the clock is provided from the inside, internally, and usually this clock glitch is not possible.
When I want to inject the fault, like a million times, what is easier to reproduce than that I get the fault always right, the power glitch or with the clock glitch?
None of them. With power glitch and clock glitch, you cannot be precise. You just make this problem for the circuit, and then you cannot say that that particular byte and that particular bit is faulty. No, you can never. But then imagine that you have AES implemented in hardware serialized. Means that one box is implemented, instantiated, and then every clock cycle, the output of this box is shifted to the shift register. Then by clock glitch, you may affect directly only one SBox computation, because all other registers which are in this shift register, they are just shift. The critical path delay for them is super short, but the SBox is longer. And then when you have the clock glitch, only the SBox output will be wrong, which affects only one byte of the state. Yeah? By the power glitch, you don't have much control, but it will be the same. Yeah? If you have a microcontroller by the power glitch, you usually have an effect on the instruction which is executed, not on entire values which are in the register bank or the memory. But if the AES round base is running and every clock cycle, all entire 128 bit of the state of the software are processed and updated, you don't have any control over the effect of them. And then there is a also more sophisticated tool or sophisticated equipment by laser beams or light beams that you can inject fault in particular part of the circuit, but you have to decap the circuit. Yeah? If you remember one of the first sessions, you have to remove the plastic cover or metal cover of the circuit to be able to access what? To be able to access the surface or silicon to be, when the laser is injected, laser beam should pass through the silicon to reach the transistors and change their state, whether they are conducting or not conducting. Something else that I did not explain you, is EMFI. EMFI is electromagnetic fault injection attack. If you remember, we had electromagnetic field and electromagnetic probes that we can use to measure EM instead of the power consumption at the top of the chip. Roughly the same kind of a probe is used again at the top of the chip, but a very high voltage is coming through the probe and makes a large field. And again, it will be a kind of a localized power glitch. It has a large effect, very strong effect on the circuit, and then it changes again the computation, then the wrong values will be stored in the register. EMFI usually is not able to change directly the content of the registers. Laser can do, but EMFI usually cannot. But if you synchronize the time that you inject the EMFI by the clock, and right before the positive edge of the clock you inject the EM pulse, then usually wrong values will be stored in the register. It means that you do not make the registers faulty directly, but the input of the registers faulty. It means that the combinational circuits which compute, they will be here, they will be faulty, and then the faulty values will be stored in the register. Again, the effect of EMFI is not that much controllable. There are some articles and some claims that you can reproduce exact the same fault if you control everything very well. But the position of the probe is also super important, where you are injecting the fault, and so on. One thing that I should mention, if you look at the first page of the slides, for example, this one, this is actually an EMF, electromagnetic fault injection setup. This is the EMFI probe, exactly at the top of the chip. It would be better to inject EMFI at the front side of the chip, means that you are at the metal side, because I'm not sure how much you are familiar with electronics, but at the top of the chip, when you design a chip, there are some power grids. Here, for example, are the VDD lines, and here there are the ground lines, yeah, at the top of the chip, yeah. And this is the grid at the top of the chip, and then every gate, which is, for example, here and here, they receive from the metal layers, they receive VDD and also ground. And then if you are injecting the electromagnetic field at the top of the chip, then you somehow inject this high voltage on the VDD lines. And then you directly affect only the gates which are here, that they are supplied by these local lines. But a laser is the other way around. A laser, you should inject the fault at the back side of the chip, at the silicon side, and sometimes you also need to make the chin thin. Yeah, it should be very thin. If it's very thick, the laser is somehow defocused afterwards when it gets into the silicon. Then you have to polish it and make it very, very thin. Then you can have a better accuracy by injecting the faults by laser beams. We have also seen some effects, yeah, that these fault injection facilities can change the execution path. As I said, you can skip some instructions sometimes in microcontrollers. You can directly change the data. Usually you change the data either directly by the register, for example, as I said, by the laser beams, or the value which is computed by the combinational circuit is wrong, and then the wrong value will be stored in the register. Yeah, these are the things that I already explained. And now we see a general fault attack. Assume the attacker can change bits of data values selectively to a defined value. First of all, we have three main models for the faults. If the attacker is able, or we assume that the attacker is able to change the values of bits to a particularly defined value, for example, to 0, we call this fault a stuck at 0. If you say the attacker can inject a fault in a way that one particular bit will be 1, then it's a stuck at 1. Yeah? And we have also toggle fault model. In the toggle fault model, you say, I don't know what the value was. Yeah, I just toggle it by injecting the fault. It means that you XOR, for example, 1 with one particular bit. Or you say, I have injected a fault on a byte, and I don't know what I changed. Yeah, but I can model this fault by XORing the original value with a delta. For example, you have x, and this is the original value. And then x prime is the faulty value. And then you say delta is actually x or x prime means that the difference between the faulty and fault-free value. And you can say by toggle fault model, you injected delta into that value. You XOR delta to this. And depending on the facility that you have and the device, if you repeat this, the delta might be the same, the delta might be different. Most of the time, you cannot guarantee that you have exactly the same delta every time that you inject the fault. And this is a trivial attack. If it's the attacker is able to do a stuck at 0 fault and a particular data values. This is also called safe error attack. The attacker performs a reference encryption with some unknown plaintext, doesn't matter, I mean, I don't need to know the plaintext even, and also unknown key. And then the attacker repeats the same encryption, but with the same plaintext. Means that you don't know the plaintext, but you can make it in a way that the same plaintext is given to the device. But then you inject the fault in a way that, okay, I set the one key bit to 0. Because I could selectively say one bit of the value is set to 0. And then you easily look at the output, If the output of the encryption changed, that means that the output of this encryption is different to that one. It means that actually the bit was 1 that you change it to 0. If the output of both of them are the same, the bit was actually 0 that you try to change it to 0. Yeah? It's a super trivial attack, and you don't need any particular model to perform the attack. Bit by bit, you can perform the attack and then recover the key. But of course, the problem is that it needs a very particular and precise fault model, and you need particular facilities to inject the fault. And most of the time, this is not possible in practice, in most of the devices, because you have to control exactly which bit you are changing, and you have to also make sure that you are doing it as a stuck at 0 or as a stuck at 1. Then for that reason, we have to get away of this model as this trivial attack model and then try to do something else. When the attacked algorithm is known, because what you have seen was completely independent of the cryptographic algorithm. It was just on some bits of the key. And then if we know the algorithm and some properties of the algorithm can be exploited to perform the attack in a much simpler way. Simpler way means that with a more relaxed fault model. No, we don't need that precise fault injections. The first attack, or DFA, differential fault attack, was published on DES 1997. Then the fault model was single bit toggle fault model. Now means that you do not inject stuck at 0 or stuck at 1, which is actually are trivial, but they were single bit toggle faults. Means that you would say, I inject a fault on one SPOC's input of this, for example, and I change only one bit, but I don't know which bit I changed. Just one bit. Means that if you remember that delta that I have written, then you can say, I'm pretty sure that the Hamming of the delta is 1. Means that I injected only one bit, but I don't know where this bit is. But I'm pretty sure that I changed only one bit, not more. And then the attack actually works at the last rounds of the cipher. This is actually a very usual thing in the DFA. Means that you target the last rounds because you know the ciphertext and you also know this faulty ciphertext, and you want to reduce the effect of fault that you inject. Otherwise, if the fault is in the middle of the cipher and you look at the ciphertext, the dependency between these faults that you injected and the ciphertext is very, very large. You don't want to have that much dependency to be able to guess part of the key. Then similar to SCA, Solution Analysis attacks, that we perform the attack either at the first round of the cipher or the last round of the cipher to be able to guess a few bits of the key. This is the same here. Then you can predict some keys and then look at the effect of the fault that you injected. Then roughly at the last rounds of the cipher, it makes easier to perform the attack. For example, the DES has 16 rounds, and then the attack works actually on the rounds 15 and also 16. And then after a couple of years, then the AES was introduced and or announced, and then most of the attacks with respect to DFA concentrated on the AES, and then many different attacks have been published on AES, and many other things have been discovered that we will see now. A part of the AES, I think this is the last paper that I know about DFA on DES, published 2009. The difference between this attack and this and the one that is actually published 2009 is that you can actually have faults at the middle round of the cipher, not only at the last rounds, but the middle rounds you can also inject the fault and then perform the attack. For example, the fault model which is used is a random bit or random byte changes. Again, toggle fault model, but bit or byte in the left register, because there are left and right register in the DES, at the end of the round 9, 10, 11, and 12. By going to the middle rounds, then you need many more pairs of the ciphertext and faulty ciphertext to perform the attack. From 1 million of pairs to 7 pairs to perform the attack. If you target, for example, round 12, then you need 7 pairs. If you target round 9, you need millions of actually pairs of ciphertext and faulty ciphertext. As I said, this will be very similar to just saying that you want to perform a differential cryptanalysis, differential attack on the round reduced version of this. And then from the last round, 16 to 9, it has, for example, 7 rounds. And then you say, I perform a DFA by this if I'm able to perform a differential cryptanalysis or differential attack on 7 rounds of this. Now we will see why it's called differential fault attack. Now we concentrate on the AES, and we also target the last round of the cipher, as you see here. And then we try to see what we can do if we are injecting fault at the ciphertext or at the input of the round key or at the input of the shift rows, input of the subbytes, and so on. What happens and with which models we can perform the attack. If we inject a fault at the ciphertext, now the question is whether we learned anything about the key. I mean, of course not, because ciphertext is already generated. Now key is not involved anymore, then you don't earn anything. Then we go up one step and say if we are at the input of the round key at the last round, and then if we inject the fault there between the shift rows and add round key, what happens? In which scenarios we are able to recover the key? This depends, of course, on the model, the fault model that we have. In the first fault model, we say the attacker can toggle one or multiple bits. Toggling fault model. For example, you have here 128-bit and then first bit LSB you want to toggle, then actually you will learn nothing. Because again, by the toggle fault model, what we say, delta is here, yeah, and the delta will actually pass exactly the ciphertext. Means that if you inject a fault with a toggle model at the first bit of the input of the add round key, exactly the first bit of the ciphertext will also toggle, completely independent of the key. No, because it's again linear, and if I have a XOR delta here, exact the same XOR with delta shows up at the output of the ciphertext. In another fault model, we say the attacker can set bits to certain values, similar to what we have seen. Again, it's like safe error attack, that you just say particular bits can be 0 or 1, then the attacker can learn the key just like the generic fault attack that we have seen on the key, similar to injecting the fault at the key. But of course, you are not injecting the fault at the key here, you are injecting fault at the input of the add round key. You make sure that, for example, the LSB is 0 here, then 0 will be XORed with that particular bit of the key, then the key comes out of the ciphertext. Means that by setting here the 1 bit to 0, then exactly you read the key bits at the ciphertext, bit by bit. Easy, yeah? Of course, this is something which is, again, super hard in practice. Then, again, we need, we'll look for something which is more general and simpler. Now, if we inject the fault at the input of the shift rows, now, as you know, the shift rows just changes the position in the bytes. And then all the statements that we gave for the attacks on the input of the add round key stay also valid when we perform the attack or inject the fault at the input of the shift rows. Now we go one step higher at the input of the subbytes. And we say the attacker is injecting some particular faults at the input of the subbytes, and under some fault models, we should be able to perform the attack. In the first fault model, we say that the attacker can toggle a bit and knows the bit position. For example, just the LSB, just single LSB. If the attacker is able to do that, actually the key can be recovered. Now, how? We see in this scenario, we assume the attacker is able to toggle just the LSB of an SBox. No? Just first the SBox of the last round, the LSB, the first bit of the SPOX input, you toggle it. Means that you don't know whether you change it to 0 or 1, you just know that you toggle it. Now for each pair of ciphertext and faulty ciphertext and each key byte hypothesis, then the attacker can calculate the SPOX input based on the ciphertext and also the faulty ciphertext, and she can check whether the difference between these two is only one bit of the LSB or not. How? Suppose that the attacked byte position of the correct ciphertext output is 1A. For example, the correct ciphertext is 1A at one particular byte that you perform the attack, and the faulty ciphertext is 99. Now you injected the fault, you change the LSB, but you toggle the LSB, and then what you do, you say ciphertext is actually 1A, and faulty text is actually 99 hex. And then what you do, you guess the key and you calculate this backwards now from the bottom ciphertext to the input of the SPOX, SPOX inverse of the ciphertext XOR key, and then you say k equals 0 till, of course, k equals FF or 255, and then you calculate the output of this SPOX inverse and output of this SPOX inverse, and then you check the difference between them. Yeah, check the difference between them is not the LSB. You see one of them for key equals 7, they have the difference of LSB. Then this, you say 7 is one of the key candidates. Usually by only one pair, you do not get the correct key out. Then you have to repeat this with another pair. And if this, it can be also under the same model, exact the same LSB, or no, even you have another model. For example, I changed now the second bit of the SPOX input. No, it doesn't matter, but usually with the same model, you need two pairs to recover key of that SPOX. Means that two pairs you need for every key byte. Then in general, if you perform this attack, then you need 32 pairs to perform the attack on all key bytes of the last round. But again, keep in your mind that this is a pretty strong fault model. You toggle, of course, you don't know the value, but you know exactly which bit you changed. You know, this is also not that easy. Now we consider another fault model, and we say the attacker can insert an unknown random fault. Even the attacker is able to say, I just changed one byte. This delta is 8-bit, exactly on one of the SPOX inputs, but you don't know which value this has or Hamming weight of this, nothing. The delta can be anything. Then you cannot perform any attack. Why? Because if I get back here, what we checked here, we said whether they actually have difference only in one bit. If you don't make any restrictions for the delta, delta can be anything from 1 to 255. Delta cannot be 0, yeah? Because when the delta is 0, then actually ciphertext and faulty ciphertext are the same, means that you did not inject any fault. The delta between 1 and 255 are possible, then any of them, difference between them, will be anyway one of these 1 to 255, and then none of these key candidates comes out. No? And doesn't matter how many of the pairs of ciphertext and faulty ciphertext you have. Now, if we have a more general fault model, the attack does not work. Now we go one step higher at the input of the add round key, which is now at round 9. Everything that we said for the input of the sub-bytes work for the input of the add round key as well. One important observation is that given an induced fault before this operation, it holds that the difference between the faulty encryption and the correct encryption is the same before and after the add round key operation, because this is the linear operation. When you model the fault by delta at the input of the add round key, it will be the same. We can imagine the fault is actually injected at the input of the SPOX with the same delta. We will use this later, we will see. Now we go one step higher at the round 9 and input of the mix columns. And this is actually a very well-known attack, and this was the start of doing a lot of other attacks. And This is the main DFA, which considers a more realistic fault model, published 2003. This is actually called differential fault attack technique against SPNS structures with application to AES and some other ciphers. Let's see how the attack works. Suppose that the attacker induces a random fault, again, very, very general fault model, on the first input byte of a mixed column. Means that what you just here restrict or limit is that you say, I just inject a fault that I don't know what it is, but I'm pretty sure and I can guarantee that its effect is restricted to only 1 byte, similar to what we discussed today. You have the serialized version of the AES in hardware, and then you just inject a clock glitch in 1 cycle, then 1 Sparks output at the last round, for example, will be faulty. Then you can control the effect of fault to be restricted to only 1 byte, not on several bytes of the position that you are injecting the fault. But now we are concentrating on the input of the mixed columns at the 9th round, means that this is the last mixed column of the cipher. And similar to what I explained, if we model this as a bitwise difference between the faulty and the fault-free values, then S1, if you can see the, again, mixed column with S1, S2, S3, and S4, the input of the mixed column. Then you say just one of them, S1, now changes to S1 plus delta, and the plus is XOR. Now, if we write this down, mixed column of S1 plus delta, S2, S3, and S4, if you remember, mixed column was a linear operation, then this is the definition of a linear function again, that the mixed column, the original mixed column, XOR the mixed column of delta and 0 and 0 and 0. Means that this is again the original value. This is the fault which you model it at the output of the mixed column. Means that you injected a fault at the input of the mixed column. You model this fault at the output of the mixed column by this. And we know that there are 255 cases for the delta, again from 1 to 255, excluding 0. And then we have also 255 cases for this 32-bit value, because this is a column. This has 32-bit value, but there are only 255 cases for this 32-bit value, not all 2 to 32 cases. Then, most likely, all 4 bytes of the ciphertext will be faulty. The AES, again, if you remember, if you look at the ciphertext, and then this is the mixed column, the last mixed column. The input of the mixed column, for example, I make here faulty. And then the mixed column output. All these 4 will be faulty. Then because of the shift rows, these faulty values will show up like this in 1 column. Means that if you look at the ciphertext and compare it with the faulty ciphertext and you see that these bytes are faulty, then you're definitely sure that only 1 mixed column is faulty. Now, of course, what we do, we do not consider this. We suppose that we know the indices. For example, this is C0 and 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10, and so on. And then you know exactly which indices you have to put together to show it as a 32-bit value. And one fact is that all 2 to the 32 possible values for the corresponding 4 key bytes, for the round 10, keep in your mind here. We actually attack here this last round key. And what we will see later, this is completely ignored. And what we are doing here is independent of the value of the at round key as this model. Because what we said that delta is the fault which is injected here, And here is actually the mixed column of delta and 0 and 0 and 0. Because of the add round key, we can also model it as a mixed column of delta 0, 0, and 0. Then it's completely independent of the round key 9. And then we are trying to perform the attack here. Now, how the attack works, the attacker makes a list of the Spock's inputs. We have just seen the Spock's inputs. The mixed column of delta and 0 and 0 and 0 should be the difference at the input of the Spock's at the last round. And then the attacker makes a list of those Spock's inputs that lead to one of these 255 cases. It's exactly the same as what we have seen. We have seen for when you inject a fault at the input of the Spock's, but one single bit. When you calculate backwards, you compare the input of the Spock's for the faulty software-text and fault-free software-text to check whether the LSB is toggled. Now you do exactly the same thing. You compute backwards to check whether the input of the sub-bytes at the last round fits to this mixed column of delta 0, 0, and 0. But 4 Spock's together. If a unique key remains, then of course, similar to before, the attacker needs to repeat the attack using another pair. You have the software-text, but as C1, C2, C3, and C4. And as I said, we ignore the indices, and we suppose that here, this is the software-text, and here is first one, and this is the second one, third one, and fourth one. Now this we call C1, and here C2, and here C3, and here C4. We suppose that, okay, they are just those corresponding software-text bytes that we concatenate together. Then C prime, we also model as C prime 1, C prime 2, and C prime 3, and C prime 4. We don't look at the difference between them. Delta between them we don't need. But what we do, we guess the key. And key is K1, K2, K3, and K4. Keep in your mind, they are the key bytes where at the last round of the cipher. But again, corresponding to these indices. Here, 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 and here. And what you do, you say, okay, a box inverse of C1 XOR K1 and a box inverse of C2 XOR K2 and a box inverse of C3 XOR K3 and a box inverse of C4 XOR K4. Now you calculate the same for the C prime with the same key. You guess the key. This has 2 to the 32 cases. You guess one of them. And box inverse of C prime 2 XOR K2 and a box inverse of C prime 3 XOR K3 and a box inverse of C prime 4 XOR K4. Then you XOR them together. What you get, let's say, D1, D2, D3, and D4. And then what you check whether this belongs to a set of mixed column of delta and 0 and 0 and 0 in a way that delta belongs to what? Belongs to 1 till 255. If this belongs to this set, then what? Then this key is one of the key candidates. If not, you check the next one. And usually a few key candidates remain, and you need to repeat this with another pair of this. What is hard? The search space is 2 to 32. No? Instead of everything that you have done till now with usually searching for 8 bits, now you have to search for 32 bits. Now you can optimize this by making it progressive. Instead of searching for 2 to the 32, then you search for 2 to the 16, the first 2 bytes. And then you check if these key or some key values lead to something which is correct. Then you continue this and you add one more key bytes to this and then perform the attack again and again. This way, the search space gets decreased, and of course, you can run the attack much faster instead of guessing 4 bytes at the start. How to do so? Look here, you guess now only these 2. And then what you check, you only check whether this belongs to first 2 bytes of this set. No? Then if you found some of them, then you make a group for K1 and K2, and then you add K3, means that you will have 256 cases for K3, and then those many candidates which remain for K1 and K2. And then you continue this again, you check whether these 3 belong to the 3 bytes, the first 3 bytes of this set, and then you make now another set for K1, K2, and K3, and again for 256 cases, and the remaining candidates here for K1, K2, and K3, you check now 4 bytes. Now you check then the 4 bytes here, and then the result of the attack will be exactly the same. You may ask, why do I not search for only K1? Why I should search for K1 and K2 at the same time? If you do it, you do not reduce the key space at all. Because look here, K1, if you just check K1, all 256 cases for K1, then you look at here and you actually just check whether D1 belongs to one of these 255 cases only at the first byte. Then you remove no candidates. Now, because the first byte of this will be 255 different cases. If you write down the formula for mixed column, which is just multiplication by 2 and multiplication by 3, each of this multiplication by 2 and multiplication by 3 is a bijection. And then what remains is just 0 and then multiplication by 2 and multiplication by 3 by delta and the delta itself. And then the first byte of this result of this mixed column, the first byte covers 255 cases. Then you remove no candidates. Then for that reason, you have to check the combination of them, which is now 2 to the 16 cases. Now you reduce it a lot because you have only 255 cases here. Now, the attack actually can be extended. Assume the attacker induces a random unknown fault in 1 byte of the AES state, somewhere in the computation between the mixed column in round 7 and mixed column round 8. Means that here it doesn't matter at all. You just inject fault and you don't know where, but you know that, okay, its effect is limited to 1 byte. And then what happens? 1 byte of here will be faulty, and due to this mixed column, this will be actually extended to 4 bytes. And because of this shift rows, it will be then propagated to 4 different columns, and it means that you injected the fault on 1 byte of every column, but you don't know which byte of every column. Suppose that I make here faulty. I don't know. For example, I made that one faulty. Through the mixed column, this becomes fully faulty, due to this mixed column. And due to this shift rows, it becomes so faulty. And because of this mixed column, of course, then it means that you injected a fault on this byte of this first column, this byte of the second column, this byte of the third column, and this byte of the fourth column. Then you need to make your model a bit different. For example, we had mixed column of delta and 0 and 0 and 0, but you say this set will be actually this, and mixed column of 0 and another delta and 0 and 0, and mixed column of 0 and 0 and another delta, and mixed column of 0, 0 and 0 and another delta. Yeah, then 255 plus 255 plus 255 plus 255 means that this becomes larger. Yeah, the set that you had, just 255 cases, now 4 times 255, and usually you need a bit more pairs of ciphertext and faulty ciphertext. If you make this model more general, then you need more pairs of ciphertext and faulty ciphertext. If you make this model super specific, then with even 1 or 2 pairs, you are able to recover the key. This is what I already explained. It always holds that only one input byte of each mixed column operation in round 9 is affected by the attack. Then the attack, as described as before, can be applied for each of the 4 mixed column operations in round 9 and so on. And this is super important. And usually 2 pairs, just 2 pairs of faulty text and ciphertext are required to recover the entire key. Because you inject a fault somewhere here, the effect of this will be in a way that only 1 byte of the first column is faulty, and only 1 column of the second byte is faulty, and only 1 byte of the third column is faulty, and so on. And then you can use this model to perform the attack. The attack is super powerful, but there are still some improvements. Even in 2009, there was another attack which showed actually this can be even more improved. I mean, the key can be exploited computationally more efficient. This is what we have seen, this delta. The fact here is that we have to limit this set. If you do not make any restrictions for this set, you cannot perform any attack. Means that I can say I injected a fault at the input of the mixed column, and this was the model. As you see, just 1 byte is different, and I knew that, okay, the first byte was faulty. As you have seen, you can make it more general and say 1 byte is faulty, but I don't know which byte. You can also say that 2 bytes are faulty. Then you can make this model as, say, mixed column of delta 1 and delta 2 and 0, 0, if you know the position. If you don't know, then you have to actually add to the set other cases, not delta 1 and 0 and delta 2 and 0 and many more, that the 2 deltas exist at every byte. Or you can say not only 2 bytes, either 1 byte or 2 bytes are faulty. Then you have to add this one and also the other ones that the delta was here and also here and here, also add to this set. Or you can say up to 3 bytes are faulty. You can also do that. But when you say all 4 bytes are faulty, that's okay. You say mixed column of delta 1 and delta 2 and delta 3 and delta 4, and you say delta 1 does not equal 0, delta 2 does not equal 0, and delta 3 does not equal 0, and delta 4 also does not equal 0. That means that all 4 bytes are faulty. Then you can still perform the attack, although this set becomes very large and you may need, I don't know, 100 of thousands of pairs of ciphertext and faulty ciphertext. But if you say, no, there is no restriction. From 1 byte till 4 bytes can be faulty. Everything is possible. The only thing that you exclude is 0, 0, 0, 0. Means that this set becomes 2 to the 32 minus 1. Then you cannot perform any attack. Any delta that you get, it belongs to one of them. for all key candidates. Then the thing is, you have to make some limitations, some restrictions. If you don't make any restrictions, then the attack will not be possible. And if you make a very specific model, then the attack will be easier possible, means that you need a few number of pairs of ciphertext and faulty ciphertext. If you make the attack more general, for example, saying from 1 byte to, up to 3 bytes are faulty, but you exclude the 4th byte. You may say, never all 4 bytes are faulty. I can restrict, for example, the effect of the fault and say, I don't know, I may change 1 byte, I may also change 2 bytes, I may also change 3 bytes, but I'm pretty sure that 4 bytes are not faulty. Then still the attack is possible, although with many pairs. And this is the effect of having a general fault model or a very specific fault model. Now, there are other attack types, not only DFA, not only differential fault attack. The safe error attack is something that you have seen, we discussed. Super trivial attack by sticking part of the encrypted cryptographic secret or intermediate values to a known value, to 0 or to 1. There is another type of attack which is called collision fault analysis. You run the cryptographic operation on 2 very similar inputs. Now, for example, 2 plaintexts, and the plaintexts are different on only 1 byte of the plaintext. Plaintexts are exactly the same, just 1 byte of the plaintexts are different, and you induce a fault near the beginning of the operations, not the last round. Because many people said, let's just protect the last round of the cipher. Last, for example, 2 rounds, then the DFA will not be possible, or the fault attack are not possible. But now this is an attack which shows that you have to actually protect the first round as well. But how the attack works, you induce a fault near the beginning of one of the computations. For example, you have the plaintext, which is given to key, and then a box. Suppose this is 1 plaintext byte, and all other bytes of the plaintext are the same. Just the first byte are different. It's stored with the same key, and it goes to this box. And then you inject the fault here. When you give P prime with a known delta, you know the delta between them. And then you just change single bit of here. You know that, okay, I toggle a single bit, and I know the model. And then what happens, then for some P prime, difference between them should be only 1 bit. Means that if the difference of them is only 1 bit, and then you toggle that bit, what happens, the rest of the computation of both encryptions will be exactly the same, then the ciphertexts will be the same. Now you are looking at the collision at the output, collision at the ciphertext, without injecting the fault. This is, for example, let's say T, and this is T XOR 1, just 1 bit is different, suppose at LSB. And if you inject the fault here at the LSB of this and toggle it, then it becomes T. And since we said all the other plaintext parts are the same, the ciphertexts will be the same. And then you know that these 2 encryptions, P and P prime, they had only 1 bit difference at the output of this box. Then you search for the key the same way that we have seen, and then you get the key out. Of course, you may have more than 1 candidate. Then a statistical fault attack. Statistical fault attack. They consider stuck at 0 fault or stuck at 1 fault. And then they look at the intermediate values of the cipher by guessing the key, and they calculate the squared Euclidean imbalance, or SEI, to identify the correct key guess. First of all, what is the Euclidean imbalance? Euclidean difference. I just talk about multivariate version. Means that you have 2 vectors, for example, x and y. This has x1, x2 till xn, and y has y1, y2 till yn. 2 vectors. You want to get the distance between them. And distance is actually calculated easily by a square root of x1 minus y1 square plus x2 minus y2 square plus xn minus yn squared. This is called Euclidean distance, yeah, or difference. And then a squared Euclidean difference or distance means that you remove this. This is the squared Euclidean distance. And now a squared Euclidean imbalance means that you have a distribution, something like this. Yeah, histogram. Yeah, this is what you have learned already. And then what is a uniform distribution? Means that all of them should be roughly like this. And then you get the squared Euclidean distance between this distribution and the uniform. This will be the squared Euclidean imbalance, which is actually similar to what we have seen before as what? Entropy. Yeah, entropy examines what? Examines uncertainty. If it's uncertain, it's close to what? Close to uniform. And if it's uniform and close to uniform, it has the higher entropy. Now, when the squared Euclidean imbalance is higher, means that it's far away from uniformity, means that the entropy is very low. Yeah? We can also consider entropy. But what the attack does, it considers stuck at zero, for example, and in the middle of the cipher, for example, again, somehow close to the last round, and then it actually looks at the faulty values, and it doesn't need the fault-free values. It doesn't need to compare, the faulty values with the fault-free values. It just looks at the faulty ciphertexts and knows that, okay, all of them should have the input of the SPOCs at the somewhere just zero, because you injected the stuck at zero fault. And then what you do, then you calculate backwards for the key candidate and look at the distribution of the SPOCs input. And then check whether this imbalance is higher or not. Means that actually the entropy is lower or not. If the entropy is very low, means that you actually selected the key correctly, because all of the values at the SPOCs input should have some stuck at zero. But if you select the key in a wrong way, then it will be randomly distributed. It will be close to uniform, means that the imbalance is lower, means that the entropy is higher. This is the first statistical fault attack that has been introduced, and it uses also the SEI, or this imbalance or entropy. But then this also needs a pretty strong, again, fault model by a stuck at zero. For that reason, the attack is improved to something else, which is called SIFA, statistical ineffective fault. But before explaining the SIFA, or statistical ineffective fault, let's look at the meaning of ineffective fault attack. Yeah, ineffective fault attack is very similar to safe error attack. For example, stuck at zero is injected at a certain intermediate bit, not at the key bytes or key bits. No? The safe error, we had the fault directly on the key values. But here we have the stuck at zero on a certain intermediate bit, for example, again, a SPOCs input, a SPOCs output, somewhere in the intermediate values. And if the result is faulty, that bit was 1, otherwise it's 0. If this intermediate bit is at the start or end of the computation, then the associated key can be calculated easily. You force one intermediate value, one SPOCs input at the last round, for example, to 0 LSB, and then you look at the output, and if the output is not faulty, means that the computation is completely correct, everything is fine, then you know that that bit was 0, and then you guess the key backwards to check whether the SPOCs input has that bit 0 or not. If it has, then the key is one of the key candidates for you. For that reason, the attack is called ineffective fault attack. And it can be also not at only at the last round. You can go a bit further in the, for example, round 9 of the AES, but then you have to guess a larger number of the key. Now, a statistical ineffective, you can actually run it by also effective. Yeah, I mean, but at the moment, let's just call it CIFA, or a statistical ineffective fault attack. Generalizes these processes and combines ineffective fault attacks and also a statistical fault attack. And we will see now how the attack works. It has a very rough and general fault model, and it usually works even if you don't have a very precise fault injection model. For example, what we have considered, okay, we inject the fault on one byte, and the fault should not actually affect other bytes. Yeah? But in CIFA, you can ignore this. We will see now. Or this attack needs a stuck at 0 or a stuck at 1. The statistical fault attack also needs stuck at 0, stuck at fault, but CIFA does not need this. I mean, even it can work with toggle fault model. We will see later error detection facilities that you can add to the system, to the implementation, that the error is detected to provide security against these kind of attacks. But unfortunately, this does not provide any security against CIFA. I mean, if you have error detection facility, you will see it doesn't provide any difficulty for CIFA. There is another type of attack. We will discuss about this in more detail in the next slide, for our CIFA. But before explaining CIFA, I need to also tell you something about the fault sensitivity analysis. It deals with the clock glitch. It's very similar to what I have explained to you before, considering the circuit as a milli or more machine. And then by clock glitch, then some values of the combinational circuit will be faulty and some others not. This is the last round of the AES. Yeah, and then what you know, there is a shift rows, and then there is no mixed column, and then there's sparks, and then here this guy, and here this is the way, and you can model it as this, that there is a register. But then if you have a clock glitch, from here to here, then you change it to this. Then instead of this period or duration, you have that one, which we call it D prime, and it was D, and D prime is smaller than D. And then what we said that if this D prime is a bit smaller than the critical path delay, for some values, this time is enough for this to be stored here. For some other inputs or some other computations of the sparks, this time is not enough. Then, for example, you set this D prime in a way that, for example, roughly 90% you get fault-free outputs. And if you inject this at the last round of the AES, you exactly know which box becomes faulty, because at the last round of the AES, there's only a box at round key. There is no mixed column in between. And you see first byte of the software text is faulty, you know exactly which box was faulty when you are at the last round of the AES. Then you know that this is faulty, but not for all values, not for all software texts. For example, with a few software texts, this is faulty. Then you can calculate this backwards again, and then only for faulty values. And you don't need the faulty value, You just need to consider for which fault-free software texts, when you inject the clock glitch, the value of here will be faulty, and you consider that fault-free value. You guess the key, calculate backward, and then you get the box input, and then again you make a distribution. Similar to a statistical fault attacks, or you make a model and do some kind of correlation, which is a bit strange here. But if you consider some bits of here or Hamming weight of this box or any model and distribution, then the attack will work. I don't explain this fault sensitivity analysis extensively because this is also covered by one of the papers assigned to you. Why I actually explained the fault sensitivity analysis for you, because if CIFAR is conducted by a clock glitch, it can actually be seen as a generalized form of the FSA, because in FSA, original FSA correlation is used similar to CPA. We will see in one of your presentations. You make a model, a Sparks input, Hamming weight of the Sparks input, or the bits of the Sparks input, and then you run the attack. But it's actually looking at the distribution of the input of the Sparks, for example, and it's similar to CIFAR. And if you run the CIFAR by clock glitches, is seen as a better way of explaining why FSA works. Now, the concept of CIFAR, how this works, it does not require precise fault location and works with any type of the fault, even if the fault is unknown. And it can defeat popular fault countermeasures like fault detection and infection. There is also a countermeasure called infection countermeasure. Means that it detects the fault, but instead of sending out a message to say that, okay, the fault is detected, it sends a random data as the output. And then you cannot actually perform a DFA, because in DFA, you need faulty ciphertext and ciphertext together. And if the random data comes as a faulty ciphertext, which does not fit to your model, then you cannot perform the attack. But of course, it provides security against DFA, but it doesn't provide security, for example, against CIFAR. It also works for some mask implementations. It's sometimes, not necessarily always, faulting one share of the mask implementation is enough to also perform the same thing, if similar to performing the attack on unprotected implementation. But usually on mask implementations, you need larger sets of faulty values to perform the attack successfully. It's mainly applicable to symmetric ciphers and also to some authenticated encryption schemes like stream ciphers and also sponge-based schemes now for the AE or authenticated encryption. But we do not consider that much here. I mean, I show you one example only based on the AES. Before that, we need to agree on this concept together. Suppose that you have one AND gate here, and suppose also that the operands are uniformly distributed. They are from uniform distribution. Means that here A, 0, and 1, the same number of times, this is the distribution, and B, the same number of times, again, distribution or histogram of being 0, B being 1. And if you give this fully uniform data input to the AND gate, this is the distribution of the output. Now, suppose that we flip the first operand. We just flip the first operand. We make a fault and make the A faulty by toggling. If we look at the output here, and of course we can compare the output with the fault-free output. If we just consider the fault-free outputs in the cases that we injected the fault, we toggled the A, but the result of the AND was not faulty, we know for all of them, B actually was 0. Why? Keep in your mind that we are toggling A. If the fault-free value is 1, fault-free value means that B was 1, A was also 1. And when we toggle A, then definitely those values which were 1 will not show up anymore at the fault-free output. Then all of those which were 1 will become 0. But then all of them which were 0 will stay also 0. Why? Because they were 0 because of B, for example, and they also stay 0. It doesn't matter if we flip A or not. Then it means that if we flip A and we look at the output and we see the output is not faulty, we know that B was 0. And this bias distribution actually can be exploited. If we do a random fault on the first operand A, again, random fault, and then considering only fault-free outputs, it leads also to a bias. Bias distribution for B. It's not that strong that we only flip the operand A. we just said we have an fully unknown random fault, means that every time it's set to 0 or set to 1 or toggle. No? If we consider also such a case, and we look at also again fault-free outputs, we find out that these fault-free outputs, there is also a bias here for B. Now this is the same concept as I explained. If you follow this backwards, we will get this. That actually we are dealing with this guy. This is also happens because the fault model is random. This happens as well, but this is the case, or this is important, that they are not uniform anymore. CIFA tries to exploit this, that if you inject some fault, and then if you look at again only the cases where you injected the fault, but the result was still correct, means that the fault was ineffective, then some intermediate values are imbalanced. This is the imbalance. I mean, you concentrate, even the random fault, you concentrate only on fault-free outputs. Means that you inject a fault, you look at the output, you see this is correct, you say, okay, this belongs to correct group. You inject the fault, again with another input, the output is faulty, you threw it away, or you put it in another group which is called effective fault. You repeat this till you have a large set of the values of the inputs of plaintext or ciphertexts. I mean, if you consider the attack at the last round, only ciphertexts are important for us. Plaintext we don't need. You put the correct ciphertexts that you injected the fault for them, and they didn't lead to any faulty output. Means that they were ineffective. And if you consider this set, the intermediate values of this set, there is an imbalance in between. Now there is a bias inside. Now we use the same concept, and we say over multiple encryptions, state bytes are actually uniformly distributed. Each byte individually, you say, is uniformly distributed. If you have many plaintext and ciphertexts, of course, you can say every column is uniformly distributed. And then we inject the fault here, I mean similar to before, and between 8 and 9, between the mixed column of them. And then, of course, the non-uniform distribution happens and there. But then we look at only, again, ciphertexts that the fault for them was ineffective, and we put them in a group. And then what we do, we compute this backwards, again, by guessing the round key here. And we look at the distribution of, again, one column, because of this mixed column here, right? Then we compute the distribution of this guy, and this guy. And again, the entropy of this distribution, or again, what was it? SEI of this distribution should be away from the uniform if the key is correctly selected. And this is done on the ineffective faults or ineffective set. You can do exact the same on the effective set. But of course, using fault-free ciphertexts means that for CIFA, you don't need to have the faulty outputs. You don't need to have faulty outputs. You need just the fault-free outputs, but all of them should belong to a group of ineffective, or all of them should belong to effective. This is the attack, for example, doing it here, but you can also inject the fault here at the input of the subbytes. Then the fault model cannot be, again, unknown. The fault model should be also restricted to a smaller set. You can say that, okay, I have a fault, but I don't know the value of the fault. This is somehow a random fault. But then what you do, you compute again here, similar to here, backwards by guessing one key byte and looking at distribution of the SPOX input. But the fault model should be in the way that if it's fully random, you don't have any information about this, about the fault, and every time that you inject the fault, the effect of the fault is fully random, and probably the attack does not work. It means that somehow the effect of the fault should be controlled. It means that you inject the fault here. You may also make all of the SPOXs faulty. It doesn't matter. But the effect of a fault should be like this, that somehow this delta that we consider together, should be not all 255 cases always. Even there is a bias there for the delta is enough to recover the key. But of course, keep in your mind that CIFA does not work like DFA with just 2 or 3 pairs of the faulty and fault-free ciphertexts. You usually need a larger set because you need to look at the distribution, because we guess or estimate the entropy, or we calculate the SEI. For that, we need to feel these bins, the distribution. Then for that, we need a larger number of fault injections. And then this is exactly the reason that the fault detection mechanism do not help with respect to contracting against CIFA, because CIFA just needs to know whether the fault was effective or ineffective. You inject the fault, the device tells I detected the fault, then you throw away everything. Until it doesn't say I detected the fault and the output is also correct, and you put this value to the ineffective set, and again you repeat this again and again until you have enough number of samples into the ineffective set, and then you run the attack. This is the key recovery phase that I already explained. You compute backwards and look at the distribution either by SEI or entropy to find the correct 32-bit of the key. When you want to provide security against these kind of attacks, you need to add redundancy. This redundancy can be timing redundancy, we will see, or area redundancy, or a combination between time redundancy and area redundancy. And this concept, resistance against fault injection attacks, is closely related to the design for fault-tolerant systems. I'm not sure whether you have seen such a things before. In digital electronics, sometimes it's required to build the circuit or circuits in a way that they still perform correctly in presence of noise, in presence of faults. For example, the devices, circuits that they are implemented or used in airplanes, they should be definitely fault-free. And then you need to improve the reliability of these circuits, which are not necessarily related to cryptography or security. You just need the higher reliability. And the researchers try to increase the number of fault coverage, number of cases that the fault can be recovered. But here in the protection against fault injection attacks, the type of the faults are very malicious, means that they can never happen in reality in the presence of noise. They might be not usually covered by the fault tolerance systems, because in the fault tolerance systems you consider a few number of faults, 1 bit, 2 bit, a few faults may happen, and then you increase the reliability, and the probability that the very strong fault happens in the system is very low. But now in the resistance against fault attacks, we have to actually cover almost everything, and it doesn't matter which kind of fault is injected, we have to provide security. In both cases, in resistance against fault attacks and also in fault tolerant system, the schemes are used usually or called concurrent error detection, or CED, that they actually try to detect or correct the fault during the runtime of the algorithm or the implementation. For example, here's something like information redundancy. And here, suppose we have a round-based implementation or any function here. I mean, it's encryption, but it can be anything. And then similar to what we have seen together, like the milli or more machine. Now, the result of the encryption, or one round of the cipher or one clock cycle, now is written back to the register, and this loop works. What you can do, you can actually predict the output of this encryption. For example, the parity bits for sure. Now I'm pretty sure. Then you can say the output of the SBoxes, you consider 1 bit parity for the output of the SBox for every 8 bit, 1 parity output. And this encode will be, the result of this encode will be 16 bits. But now you have to predict this value as well. How? The predict is actually easy. This will be actually the encryption, which is followed by the, again, encode. You may say that, okay, actually this is the same. Yeah, this is encode and encryption and decode, and this is also encryption and decode. Yeah, but you can combine them. Yeah, because all 8-bit of the boxes, you don't know if it's just a box or one round of the cipher. You just need 16 bits every bit of this box output, for example. Then you can combine this, and this circuit, this should actually become much smaller than this plus this. And then you predict what should be the output of the encryption or this round function, and then you check whether the output are correct or not. And of course, this doesn't check everything. Yeah, just a few number of faults will be detected. And I'm not sure whether you are familiar with the error detecting code. They are linear error detecting code, like Hamming code, if you have heard. Parity, for example, is one of the linear error detecting code. It's a very simple one. And you can have more sophisticated code here, not only parity bits. You know, for example, to be able to detect more bits in every byte, for example, for the AES. Or you can have some non-linear codes. You know? I mean, this is something which is also sometimes called robust codes, which is roughly similar. Yeah, I mean, this after this, instead of the encode, you have the compression and then L compress, and the cubic functions, but doesn't matter. We don't deal with that much. But this is roughly the same. Means that this encryption is already integrated into this computation. Yeah, means that this is actually again encryption and then compress and then L compress and then cubic, but you combine them together, or you predict this and then run the same as before. Then this should be generally smaller than area of this plus this, but then the error coverage will be different. Yeah, because for linear error detecting code, you can have formulas and say, okay, 1-bit error we definitely cover, 2-bit errors we definitely cover, with 3-bit errors we cannot say anything. But then for nonlinear codes, usually the number of error bits that you can recover is a bit higher compared to linear codes. Another simple thing is timing redundancy. Then you calculate 2 times. Then instead of 10 clock cycles for the AES round base, you need 20 clock cycles, but with the same circuit. Have you ever heard about majority voting? What do you do, the majority voting? How many instances you need? At least 3, yeah? To what? To correct. Here is just to detect. With 2 instances you cannot, or 2 times running this, you cannot correct. You can just detect. But that, as I said, nowadays in research community, error detection is not enough because CIFAR can overcome this. Then you have to do something like correction. Then the easiest correction is to run the scheme 3 times. For example, you have the AES, again, mask AES. You run it once. You run it again with the same plaintext but with another mask or different sharing. And you run it one more time. And then you check at the end whether everything is correct or not. But keep in your mind, yeah, if you do the majority voting just at the output of the cipher, bit by bit, it doesn't really recover anything. Yeah, because if the middle thing happens something, you cannot correct something at a ciphertext. It means that every step of the computation or every clock cycle you have to do the correction, like here. Yeah, it means that 1 clock cycle, the result goes here. At the same time, you store it here, and the next clock cycle you also calculate the same thing, and then you compare. For majority voting, you need to have 3 registers and then do the correction here for every clock cycle. Or you have error redundancy, then you instantiate the circuit 2 times at least. Yeah, and then at the same time, you check whether the results are correct or not, and you have 3 instances of this, and then you correct, or even each instance can have its own register. For majority voting, for 1 fault, 3 instances you need. For 2 faults, you need 5 instances, and so on. And actually, the majority voting is also one of the linear codes that you can also use for correction. They are the simple thing, simple scenarios to provide security against these attacks. But as you can see, either you increase a lot the latency or you increase a lot the area. There are some hybrid countermeasures that you can use. For example, if you have a function here, then you have the inverse of this function for the next clock cycle. It means that the first clock cycle you have here the value in x. While you do the encryption, you store this value into the register y. And then next clock cycle, you store the value into the register x. But at the same time, you do the decryption, the inverse of the previous computation of the last round, and then compare the result. It means that if you need 10 clock cycles for the AES, using this, you need 11 clock cycles. What is the problem of this guy? Now, if you inject a fault here and a fault here, exact the same fault here in both cases, then it cannot be detected, or it cannot be corrected. Of course, in reality, it might be hard, but using clock glitch, it might be possible. Because the critical path delay of all these instances are very similar together, particularly if they have the same net list and they are just placed and routed inside the circuit differently. By clock glitch, you may overcome the duplication, because it's called duplication. And if you have a permanent fault here, it can never detect the error, because every time that you run it, you always generate the same faulty output. Of course, afterwards, if you have a permanent fault, it cannot deliver the correct output anyway, never. It means that you have to give all the plaintext that you want, and then you inject a permanent fault, and then you give exact the same inputs that you have given before now again to get the faulty values. But of course, as I said, the device does not work anymore correctly because it's a permanent fault. And then there are some other cases, because of this, you have area and also a bit latency overhead. If you are able to put some functions that they are transparent to this operation, you can apply this before and after this encryption and also randomly. For example, you can consider that every column of the AES is calculated or processed individually, because there's a mixed column and the shift rows. Then you can say that this is my state of the AES, and this is the first column, and this is the second column, and the third, and so on. If you swap these columns, of course, you need to swap the key, round key as well. Then the result of the computation will be the same if you apply the inverse of this swap at the end of the encryption, end of the round function. Means that here, by this function P, you swap them. For example, you swap column 1 with column 2, or you randomly select how you swap them, and you apply the inverse of this swapping at the end, and then you don't need to spend anything here. And if it's hardware, then this swap is also not fully for free because you need some multiplexers, but area overhead will be, of course, much smaller than considering this. Then if you have a permanent fault, then this is able to still detect the fault, because not always the fault, which is actually here on this box, it not always processes the first column because you swap them from here and swap them back. Sometimes it processes the first column, sometimes the second column, sometimes the third column, and so on. Let's see this example for the AES. It actually supports encryption and decryption both, and they are actually registered here. First, plaintext XOR key is stored in the register, goes to the shift rows and subbytes. You know that shift rows and subbytes you can swap. And then the result will be actually stored in the same register, but at the same time, the 0 is stored here. And the next clock cycle, the 0 was here, the output of the plaintext XOR key. And here at the right side, you do the mixed column and add round key. But here at the left side, you perform before shift rows and S box. Now you compute the inverse of them. Inverse of the shift rows, first row does not change. Third row is also the same in the inverse of the shift rows and the shift rows, because you shift 2 bytes either to the left or to the right will be the same. Just the second row and the fourth rows will be different. Again, you remember how the SPOX is built. Inversion in Galois field affine transformation. If you keep the inversion the same, you can have inverse of the affine transformation at the top, and then with some multiplexers you can implement both a SPOX and a SPOX inverse, because the inversion is the same. Then for a small overhead, you have the SPOX inverse and a SPOX itself. Here means that here you calculate what you have done backwards, then to compare, and then next half of the cipher round is executed here, and the next clock cycle again here normal, and here the inverse of the mixed column. Of course, the overhead of this circuit is a bit high, but it supports both encryption and decryption. What is also important is that the output of the key generation should be also checked. We have to check whether the key scheduler is also working correctly. What you can do easily, or what they have done, they pre-calculated K10 first and store it in the register, and then the last round of the cipher, they check whether the last round key is the same as the previously calculated last round key. You can detect the fault. But as I said, all of them are the fault detection, and they can provide security against DFA, but not against sophisticated attacks. And then every round of the cipher is executed in 2 clock cycles, because half of the round here and another half here. And it takes, I think, 1 or 2 clock cycles, more than 20 clock cycles to produce the ciphertext when you give the plaintext. There are many more things to read if you are interested. There is something that we have done roughly 5 years ago called impeccable circuits, a mechanism to guarantee the detection of faults, because what you build based on the error detection codes in hardware, you assume that, okay, you build something which detects any fault, but then your assumptions may not fit into the reality, and there are some rules that we have defined how to avoid these problems. For example, you inject a single bit fault, and the error detection code that you have should recover every single bit fault, but the fault is actually propagated to more faulty bits, and then it's out of the capacity of the code that you have integrated. And then there are some rules there how to implement the circuits with error detection codes to avoid this fault propagation. This is something that I explained. Fault detection schemes cannot provide protection against CIFA. One solution to that is error correction. This is another version of this impeccable circuits, impeccable circuit 2, that how to integrate error correcting code inside the hardware circuits to provide security. One other thing that you can do that is actually not covered here is that to avoid any fault to be ineffective, means that any fault which is injected should be effective. This is one way. Integrating some sensors into the circuit is also one way, which is completely independent of the circuit. For example, sensors which detect clock glitch, sensors which detect power glitch, light sensors to detect the laser beams, or some coils inside the circuit to again detect the electromagnetic pulses and so on. But they are not algorithmic level countermeasures. They are just circuit level countermeasures. So they are completely independent of any circuit that you have, any algorithm, mask, unmask, and so on. One more thing that we have seen protection against side channel. We have seen protection against fault injection attacks. But if you do all of these things, there are still attacks that are a combination of both active and passive physical attacks. Means that you inject the fault and at the same time you measure the power consumption. And none of these countermeasures can provide security against those kind of attacks. For example, you inject the fault by clock glitch and you measure the power consumption in the next clock cycle. And then there is a facility to detect the fault, and then you just measure the power consumption of the circuit but at the end you look at the output and you see the output is faulty or the fault is detected, you throw away this measurement that you have. You collect or you save only those side channel traces that did not have any effective fault. Means that the fault that you have injected on them lead to ineffective result. The result was absolutely correct, but you also measure their power consumption and you use their power consumption. Means that the implementation is masked. It's also combined by some fault detection facilities, and then instead of performing, for example, CIFA directly on them, you perform the side channel analysis or power analysis attacks, but this classification between effective and non-effective is done based on the fault that you inject, but you don't use the result to perform the CFA because it's masked, for example, third order attack, and it's hard to perform the CFA, but then you perform the side channel attacks on just ineffective set. In general, providing security against combined attacks is not that easy. No, it's super complicated. It leads to very high overhead, either in time overhead or area overhead or both of them. And at the same time, you cannot ignore these combined attack scenarios. Most of the devices which are in the market, they have protection against faults, and also they have protection against side channel attacks, but not necessarily against the combined attacks. And I have to say that protection against fault attacks has been integrated into the products much earlier than the side channel attacks. One reason was this reliability things, but also from security perspective, you can consider that the fault attacks have been introduced to the community a bit earlier than the side channel, and the foundations of the fault attack was easier, and then companies or industry could easier integrate facilities against fault injection attacks into their products than the side channel, because it took some time till the community learned how the attacks actually work, how the countermeasures should be implemented, and so on.